Module 8.1, Translations, Simple Harmonic Motion, and Fundamental Identities. Sections 6.4, 6.7, and 7.1 in your book. In this section, we continue our study of the graphs of trig functions, and we're going to use the properties of trig functions to look at a type of motion called harmonic motion, which lots of things in the real world show. And then we're going to look at some more trigonometric properties that are going to help us make calculations a little bit easier. If you've done algebra before, you should remember what translations do to graphs, and really the same thing is going to apply for trig functions. Translations are going to affect trig functions in the same way. You should also be able to quickly find the period of any trig function. And also you should try to memorize as many trig identities as you can, but definitely be able to use the most important ones. Translations of trig functions. The graph of y is equal to f of x minus d is a horizontal translation of the graph of y is equal to f of x by d units to the right. So even though it says minus d, you shouldn't think left, you should think right. If you see something like x plus d, and this is assuming d is positive, if you see x plus d, then it's not to the right, but to the left. It's the opposite of what you would think. It's counterintuitive. So for example, y is equal to 3 sine x minus 3. It looks kind of like sine x, right? Sine x looks like that. But 3 sine of x minus 3 is going to be shifted not to the left, but to the right 3. 1, 2, 3. So it's going to look like this. And it's actually going to be higher. It's not going to go from negative 1 to 1. It's going to go from negative 3 to 3. Find the interval for one period of y is equal to negative cosine 3x plus pi. We've already done this, but let's just make sure we can still do it. Remember, we were supposed to set up an inequality. Usually the period is between 0 and 2 pi. So we're going to take this 3x plus pi, and we're going to solve for x. We're going to subtract pi from all sides. From all three sides, we're going to subtract pi. So that gives us 0 minus pi is negative pi, 3x plus pi minus pi is 3x, 2 pi minus pi is pi. Then we're going to divide everything by 3. That'll give us negative pi over 3 is less than or equal to x is less than or equal to pi over 3. That's where this function is going to repeat itself, from negative pi over 3 to pi over 3. Now whenever you're adding something to the outside of the function, right? It doesn't say sine of x plus x, but sine of x plus c, right? It doesn't say sine of x and minus c or plus c in the inside. Right. But whenever you're adding to something to the outside, it's going to be a vertical translation, so up or down, right? You're adding to the y values essentially. And this is just like you would think. It's very intuitive. If it says plus c, you move up, right? If it says minus c, you move down. If it'll let me write. So we're going to sketch a graph of y is equal to cosine x. You already know how that looks. It starts at 1, goes down, goes back up to 1, and that's from 0 to 2 pi. Right? And now we're going to sketch cosine of x minus 2 plus 1. What this is going to do is it's going to take cosine of x and it's going to move it, again, not to the left but to the right 2, so 1, 2 from its starting point, and up. So to the right 2 and then up 1. And that's going to be like the 0. So same thing for this starting point of 1. It's going to move it 2, 1, 2, and it's going to move it up 1. And that's where it's going to start. So it's going to start at 2, 2. Just like that. And same thing for this point, the lowest point, which is at -1. It's going to move it to the right 2, 1, 2, and it's going to move it up 1. So I'll bring it to 0 actually. To the right 2 and up 1. So it'll look something like this. Harmonic motion. The position of an object oscillating about an equilibrium position is given by y is equal to a cosine omega t. This thing is called omega, where t is time. And omega is just the number in front of t. Remember that we said that the period was equal to 2 pi over whatever that number is. So it's 2 pi over omega. Right, and we're also going to have a new definition. The frequency is 1 over the period. And the frequency is just the number of cycles per time, or the number of times it goes through one full rotation, or through its entire period. You can also model this position using the sine function. So we can also use y is equal to a sine omega t. Right? The cosine function always repeats itself, just like the sine function. They just start at different spots. So all of this is harmonic motion. It's motion that just goes up and down, and repeats over and over again. Right? So the idea is that we have like something like a spring, right? It's maybe attached to the wall, and you have some sort of weight with some sort of mass, and maybe you pull this mass. Right? So you stretch the spring a little bit, and then you let go so that the mass starts oscillating, starts going back and forth. Right? There's a little spring there. It starts going back and forth, and it's fixed against the wall. Right, so suppose an object is attached to a spring. It is pulled down 2 centimeters from its equilibrium and released. So now we have something that's attached to a spring. Right, so some object weighs some amount. Okay. And it's pulled down 2 centimeters. Here it's just at rest, but it's pulled down a total of 2 centimeters. And then it's released. So now it starts oscillating back and forth. And we're going to assume that there's no friction here, so it's not going to ever stop. It's going to keep oscillating, and it's never going to lose momentum or anything. Which is not true, but this is a starting example. Okay. And we know that the time for one complete oscillation is 3 seconds. So the time it takes for it to go up and then all the way back down is 3 seconds. Remember that the number of cycles per time is the frequency. The period is the number of times it takes you to go, is the time it takes you to complete one complete oscillation. So the period here is what? 3. And again, we know that the period is also 2 pi over omega. Because we're going to use the function y is equal to a cosine of omega t. We need to find omega. We need to find a. So y is equal to, what do we need for a? What is the amplitude of this function? What is going to describe the motion? Right? Again, it's released. Or it starts off at rest here. You stretch it all the way down 2 centimeters, then it's released, and it goes all the way back up, and then goes up 2 centimeters, and goes back down, all the way back up. Right? Just like the cosine function. Right? Up and down. So what's the amplitude? from the center to the top is 2 centimeters, and from the center to the bottom is 2 centimeters. So the amplitude is 2. Cosine, and again, we need omega still. And all we need to do is solve for this equation here. If we multiply omega on that side, we get omega is equal to 2 pi over 3, which is the period, which is the number in front of t, sorry. And then that's it, we're done. This function is going to model the position at any time. Recall that an identity is an equation that is always true. So we have even and odd identities. For example, we knew that sine of x is odd, so that means that sine of negative x should always equal negative sine of x. Cosine of x is even, we've already mentioned this, and that means that cosine of negative x should equal cosine of x. In other words, negatives don't affect cosine, but they do affect sine. We also have the reciprocal identities that we've already talked about. Sine of x, cosecant of x is equal to 1 over sine of x. Secant of x is defined to be 1 over cosine of x. Cotangent of x is defined to be 1 over tangent of x. So given tangent is equal to 4.9, find tangent of negative theta. How can we work this out? Well, there's an identity for that, but you don't even need that, right? Tangent of negative theta is the same thing as sine of theta, or of negative theta, over cosine of negative theta. And then here we're going to use the properties that we already know. Sine of negative theta, because sine is odd, is negative sine theta. And cosine of negative theta, because cosine is even, is just cosine theta. But what is this? This is tangent theta all over again, so that we know that this is equal to negative tangent theta. We know that tangent theta is 4.9, so this is just equal to negative 4.9. And this also gives us the rule for tangent theta. Tangent of negative theta, just like sine, is equal to negative tangent theta. And we just showed why. What about tangent of theta is equal to negative 5/3? What does that tell us about cotangent theta? Well, that tells us that cotangent theta is equal to 1 over tangent theta, or 1 over negative 5 over 3, or, since that's just the reciprocal, negative 3 over 5. So try these on your own. Give one period for the following function: 2 cosine 3x plus 2. Right? We just did that. Find the period and frequency for y is equal to sine of 2.4x plus 3. Remember, the period has to do with whatever the number is in front of actually this is not. The period is actually always the number in front of whatever can be factored out there. So here, if we were to divide this out by 2.4, just to be a little bit more clear, x plus pi over 2.4 and plus 3. Okay, again, the period will always be this number, Okay, it's still 2.4, but I just want to be a little clear that this doesn't mean you're moving it to the left pi times. This actually means you're moving it to the left pi over 2.4 times. Remember, it's only that translation we talked about is only true if we have x plus something, not 2.4x plus something. Okay, just to be clear. But yeah, the period is going to be what? 2 pi over 2.4. Right, we don't have to simplify that now. The frequency is the reciprocal, is 1 over the period, or 2.4 over 2 pi. And we're done. You're now ready to start homework section 8.1.